Welcome to Math 2320, Section 2.4. We're looking at exact equations. Now they look in a particular format, and that is they're written in this differential format where we have some function m of x and y dx plus n of x and y dy is equal to 0. Now the assumptions for all of this to work are that m and n are both continuous functions on a region R in the plane. Now some of this discussion doesn't come about until Calculus 3, so I want to be careful as we start talking about this for those of you who haven't seen this before. For this differential equation to be called exact, the partial derivative of m with respect to y must be equal to the partial derivative of n with respect to x. And so these symbols are partial derivatives. So let's see what that is. It's like a normal derivative with some modifications. So for example, the partial derivative with respect to x of x squared plus y squared. When you take this derivative, you're assuming that x is the variable and all y's are thought of as constants. So the derivative of x squared is just like normal is 2x, but the derivative with respect to x of y squared, y is considered a constant, and so that derivative would be 0. What if I wanted to take the derivative with respect to y of 3xy plus 7y cubed? Alright, so y is the variable. In this case, all x's are constants. So I'm really taking the derivative here of a constant times y. Well, the derivative of a constant times y is the constant back. The derivative with respect to y on this term is just like normal. You would get 21y squared. What about the partial derivative with respect to y of the ln of x plus y? Well, the chain rule still applies, and so the derivative of the ln of a function is 1 over that function times the derivative of the inside part. Well, if I'm differentiating with respect to y, then x is a constant, and that's 0. And the derivative with respect to y of y is just 1. What about the partial derivative with respect to x of e to the 3x plus 2y? Again, the chain rule, so the derivative of e to a function is e to that function back times the partial derivative with respect to x of the exponent part. Well, the derivative with respect to x on 3x is 3, but the derivative of the 2y with respect to x, since y is a constant, would be 0. So hopefully that gives you a little bit of an understanding of partial derivatives. If you're thinking about it in terms of a surface, then let's see if I can make a rough sketch here. So let's say we had a surface in 3 dimensions here, and I'm looking at a particular point. Then when I hold y constant, the partial derivative with respect to x gives me the slope toward the x-axis, and when I take the derivative with respect to y, I'm holding x constant, so it gives me the slope of the tangent line pointing down the y-axis. So a little bit of an understanding of partial derivatives. All right, so let's see here on question 1. Question 1, we have it written in the form, so here's m, here's n. I'd like to see if it's exact or not. All right, so I need the derivative of m with respect to y. Well, since there are no y's in there, all x's are constant, and that derivative is 0. All right, well, let's see. N of x and y is 7y plus 9, and I need the derivative of n with respect to x. But since there are no x's in there, that derivative is also 0. So what that says is there is a function of x and y where the derivative of f with respect to x is 2x plus 1, which was m, and the derivative of f with respect to y is 7y plus 9, which is n. Alright, so we get started by letting the derivative of f with respect to x equal to 2x plus 1. So I'm going to integrate with respect to x. Alright, so if I do that, I get back f of x and y is this integral. I'm integrating with respect to x, so a normal integration. Integral of 2x is x squared. Integral of 1 is minus x. Now the new part, which might seem strange, is typically I'd have an arbitrary constant of integration. Here, how would I have gotten a constant? I would have gotten a constant if the item on the end solely had y's in it, because then the derivative with respect to x would not appear. So the assumption is this integral then is x squared minus y plus potentially a function of y. And again, that's because the derivative with respect to x on this function is 0 and would not appear. All right, so holding that thought then, we're going to take the derivative with respect to y on this part. Well, the derivative with respect to y is 0, 0, and since this only has y's in it, it's our normal derivative h prime of y. Now, why does this have to equal to 7y plus 9? Well, let's see. The derivative of f with respect to y is that. And up here we had the derivative of f with respect to y must equal to n. And that's what this is. Alright, so I have h prime is that piece. So to get my hands on h, I integrate with respect to y. So I integrate 7y, I get 7 halves, y squared plus 9y plus now an arbitrary constant. So putting all this together, f of x and y. Remember, here was my first crack at it here, x squared minus x plus h of y. But now I know what is h of y, and so I get f of x and y is this with my h of y plus c. But that's not the end of the story. So our solution is of the format when this item is equal to 0, or x squared minus x plus 7y squared over 2 plus 9y is equal to some constant. And that constant would be determined if we had an initial condition. All right, so let's look here on question 2. Question 2, I've got m and n. All right, so here's m. I need the derivative of m with respect to y. All right, the derivative of the sine of the y is cosine of y. And now the derivative of this part is like a constant times y. So the derivative is I get just the constant back, which is the sine of x. N of x and y is the other piece. I need the derivative of n with respect to x. Derivative of cosine is minus sine. The derivative with respect to x, all right, so the cosine of y is like a constant times x. So I get the constant back, and the derivative of just a pure y would be 0. So I'm looking to see, are these the same? And yes, they are. Now you'll also see this notation for the partial derivatives, which is a shorter, more modern notation. All right, so we start off by letting the derivative of f with respect to y be this item. Now let's see, where did that come from? All right, let's see. I guess I did not show that. So here we have f of x and y. We have the derivative of f with respect to x is this. And so now if I integrate this with respect to x, I get x sine y. The derivative of this with respect to x gives me this cosine, plus as before we have the h of y. So taking this then and differentiating with respect to y, the derivative of the sine is the cosine. The derivative of y times the cosine, this is a constant, so I get cosine of x plus h prime of y. But the derivative of f with respect to y is supposed to equal to n. So matching up terms, I see h prime of y is minus y, which is what they have here. Is it exact? Yes, we saw that they did match. And so h prime of y is minus y. So integrating, I get h of y is minus 1/2 x squared plus c. And if I fill back in what I knew about h of y, we get our function of x and y. So the solution is of a form where f of x and y is 0, or this equals to a constant. All right, in question 3, let's see. We have m is the first part, so this is m. This is n. So I look, the derivative of m with respect to y. All right, that's a minus 6y to the 5th. N is x squared minus 6xy, so I need the derivative of n with respect to x, so 2x, and with respect to x, so a minus 6y. But pretty clearly these are not the same, therefore it is not exact. In question 4, we want to solve again a differential equation where I've got it in the format where this is m, this is n, and we're given an initial condition. Alright, so let's see, m of x and y is x plus y squared. So let's see, derivative with respect to y, bring the 2 down. The derivative of the inside with respect to y is 1, and so I get 2 times x plus y. The derivative of n with respect to x, all right, with respect to x so that the y is a constant. Derivative of x squared is 2x, and the derivative of minus 8 is 0. And so now if you compare the derivative of m with respect to y, it's exactly the same as the derivative of n with respect to x. Alright, so the derivative of f with respect to x is m. Alright, and m was x plus y squared, and I went ahead and just multiplied that out, making it easier to integrate. So I'm going to integrate that term by term, so I get 1/3 x cubed. Integrate with respect to x, so y just sits there as a constant. The derivative of 2x is x squared, and the y squared is as a constant, so I pick up x times that constant, plus again potentially a function that only has y's in it. So taking the derivative of this function with respect to y now, 3 comes down, well, the derivative with respect to y, this term is 0. With respect to y, this term is the constant, so I get x squared. The derivative of this term with respect to y is 2xy and h prime. But this needs to match up with n, and n is this item. So we compare x squared, 2xy, 2xy, so h prime has to be minus 8. So that gives me then, if h prime is that, then h is the integral of it, or minus 8y plus c. So what that gives me then is my function of x and y. Okay, so here's my function of x and y. So writing that as our solution and using the fact that y at 1 must be 1, so I fill in 1 for x, 1 here, 1 for y, because y of 1 is 1 all the way through. And when I simplify, I find out that c is minus 17 thirds.